Hey, Chloe. We're doing the second half of 4-3. So I said get to this spot where we have the confusion of the inverse, and I'm going to make a table over here. And make sure we include Chloe in our table.
No.
Okay? So help me out here. Zoop, zoop. A little four table. Get your stuff out, you boys.
I don't even have stuff.
We have juniors. We have seniors. We have boys, and we have girls. Okay. All right. Yeah, let's do that. All right, juniors, we just have two of you. There's one boy, one girl junior, right? Okay, now I got to count. 1, 2, 3, 4, 5 senior girls, and 1, 2, 3, 4 senior boys. Is that true? That's 11.
You put it the other way around. It's 4 boys, not
4 boys, 5 girls. Yes. I put those in the wrong spot. Okay, 4 and 5. There we go. Which makes boys total 5 in here, girls total 6 in here, seniors total 9, and 2 juniors. Okay, and that makes a total of 11 if we put 11 over here in this very, very, very corner. Okay, let's talk about this conditional probability thing again that we ended with yesterday. Okay, so I want to know the probability of a junior given a girl. Okay, I want to know the probability that they are a junior given that they are a girl, right? Okay, so sometimes they will write that as probability of junior with a line girl, right? Okay, this is the notation that they a lot of times will use. Junior given girl, right? So now I'm not talking about all 11 of you. I'm only talking about the girls, which are 6 of you, right? So my bottom number is girls and my bottom number is 6, right? There's 6 girls total. Now out of them, how many juniors are there? Is it 1/6 or 2/6? Because there's 2 juniors in here. But out of the girls, there's only 1. So 1/6, and that 1/6 is Hallie, right? Okay, now let's say I flip that around though. What is the probability of a girl given that they are a junior, right? Let's flip it around and let's see if we end up with something similar, right? Probability of girl given junior. So girl with a slash, junior, right? Now, still not talking about all 11 of you. I'm only talking about the juniors, which is 2, right? And of those, we only have 1, which is a girl, right? Are these 2 things related? No. Like a lot of people think that like, oh, if this is 1/6, the other one should be 5/6. No. That is the confusion of the inverse. If I invert them, if I do girls versus juniors and then juniors versus girls, the probability ends up being way, way, way different. They are not the same as each other. They don't add up to be 100%, that type of thing, okay? That is the confusion of the inverse. All right, so here we go. Let's talk about their example that they do. Confusion of inverse. Probability of B given A and probability of A given B are not the same thing. They don't even add up to 100%. They're not related. So when you flip them around, it will not be the same fraction. If it is, it's a huge coincidence, right? Okay, so here we go. We've got this going on. We've got 2 events going on. This looks like my geometry class. We have event D. They have is darkness outside. Okay, so event D is the probability of it being dark. Probability of it being dark right now is probably slightly higher than 50%, right? Because it's light from, I don't know, like 7:30, I think is when the sun actually rises right now. And when does it set?
like before that.
A little bit before that, maybe like 7, I think is when it starts getting dark. So it's slightly higher than 50% is the probability of darkness right now, right? Slightly higher than 50%. Okay, M is the probability of midnight. Midnight exactly is 12 o'clock on the dot. What's the probability of me hitting midnight exactly? Like out of all of the hours and minutes and seconds of the day. Like very, very, very slim to none, right? Do you know how many minutes there are in a day?
3,600?
3,600 seconds are in a day, I think. Minutes would be, I don't know, 60 times.
3,600 seconds in a day? That's
What is it?
36 seconds in an
1440. It's
36,
14.
blah, blah, blah.
1440.
Did you take 24 times 60?
Yeah.
Okay, 24 times 60 is 14 what?
40.
1440. So the probability of it being midnight exactly is 1 out of 1440. You see that? There's 1 minute. For 1 whole minute is midnight exactly. Out of 1440. I can't, yeah, my brain's all over the place. Okay? So this one's going to be slightly a little bit greater than 50%. This one's going to be 1 out of 1440, right? Okay, that's the probability of those things happening. All right, now, this one is saying the probability that it is dark given that it is midnight, okay? And it says we are ignoring the Alaskan winter. Do you know what Alaskan winters look like?
It's always
Long.
Alaskan winters, like in Alaska, they go from like one point in the year, it's like 23 hours of darkness, like 23 and a half hours of darkness and like a half hour of light versus like 6 months later, it's reversed. So it's like 23 hours of light and a half hour of darkness, whatever. So like on their curtains, they have like blackout curtains so that like they can actually sleep during normal hours. There's a lot of like mental health issues that go along with that because like darkness is like sad times happen in darkness, okay?
Messes up your circadian
It messes up all of the like your clock,
and you
your
can't
internal
have
clock.
all the time 'cause you need vitamin D.
Correct, which screws up things. Yep. So yeah, I'm imagining that a lot of those people need to be on supplements. Okay. So if we look at this and we say, what's the probability? If we look at this one right here, what's the probability that it is dark, given that we know it's midnight right now? What is the probability of it being dark if it is midnight right now? Close to 100%, or they say 1, right? Okay, like exactly 100% if we're ignoring Alaskan winters and all that stuff where it could be still light out, right? Okay, but what is the probability that it's midnight given that it's dark outside? So I know it's dark outside. What's the probability that it's midnight exactly?
Not very.
Probably close to 0, right? It's not 0 exactly, but it's close to 0. Now, they should have not put 0 there. They should have put 0 plus, okay? And we'll use 0 plus going forward. 0 plus is a number that we will use quite frequently throughout our calculations and stuff, going forward, especially in the next couple chapters. 0 plus means a number that's very, very, very close to 0, like 0.000000000, like 3, maybe. That would be a good usage of the number 0 plus, right? Because we're saying it's slightly higher than 0, but it's not 0 exactly. It's not impossible to happen, right? But it's a number that's really, really, really close to 0, and I want to be lazy and not write out all the zeros, so I'm just going to put 0 plus. Does that make sense? Okay. So if it's like greater than like 4 zeros, maybe you can go ahead and put 0 plus. Make sense? Okay. We will use that going forward. All right. Number 3 is something called Bayes' theorem. Let's see what we've got going on here. All right, we got to fill out a contingency table. We've done this I think we did this in Algebra 2. I know we did this in Algebra 2. We talked about the rate of cancer versus not cancer and testing positive for cancer, testing negative for cancer. Do you guys remember J.C. Himmelberg? We talk about J.C. Himmelberg a lot. J.C. would be like Jalen Himmelberg's older brother. When he was in 7th grade, it was like my first year teaching here. He was in 7th grade. And that spring, we were in track season, and I was one of the junior high track coaches. He went to the doctor because he had something like weird going on his arm. He had like a weird rash or a weird sore or something on his arm. And they thought for a moment that he had leukemia. Like he went and had his blood tested and his white blood cell count was like huge. And they said, we think this is cancer. Like prepare yourselves. You're going to be in for a long haul of like chemo, radiation, all the things, like everything. And like it was devastating. Like the junior high track kids, like we had to sit them down and talk with them about like this is what's happening to your fellow peer, like big and scary things. And up to that point, like 7th graders should not have had to deal with any of that unless they had family members die of cancer. But like a young person like that, like that was the first incidence. And now since then we've had quite a few people in Blue Hill that have had, cancers and died and things like that are young even. But like that was the first incidence of this happening, and this was like hugely devastating to our community. But then they went in and they did extra testing and things like that. You call it divine intervention, whatever. Some people think that he was like cured because of prayer and stuff. That may be true. I don't know, whatever you believe. But they found that instead of leukemia, it was actually a staph infection that had some of the same symptoms as what leukemia does present as. So like his white blood cell count was elevated because it was an infection. All these other markers that typically leukemia presents with is what he had. But they did the extra testing. They like basically tested him again, and it said like, no, that was a false positive type of thing in the beginning. And the family was like, yes, thank you so much. Like kind of similar to my situation that I had just recently. Like we were told for 5 days that my daughter had a tumor in her eye that was cancerous. And we went back in and they said, no, this is not She had 4 doctors look at her scans initially, and they said, yep, this is cancer, like, we're going to be in for the long haul. And we were ready, and then they said, no, it's not, it's benign, which we were super thankful for. But this is what happens, and let me show you why when we have false positives, false negatives, it's good to do that redundancy. Remember what we talked about, redundancy? Where we do the test again, because the chances of getting 2 false positives or 2 false negatives in a row is very, very, very small, right? So we run the test again to make sure that our results are actually accurate. All right, so here we go. This is the information that we have. Assume that cancer has a 1% prevalence rate. That is like actually a really high prevalence rate for cancer. That means like 1% of the population. 1 in every 100 people are getting cancer. Maybe that's higher than that. I don't know. 1% cancer. So they went ahead in this first bullet point and they said probability of cancer is 0.01 or 1%. Okay. They say the false positive rate is 10%. So let me just show you what that means. False positive. That means out of all of the people who do test positive for cancer, 1 out of every 10 is not actually cancer. 9 of them are true cancer. 1 out of every 10 is not true cancer. Does that make sense? So 1 out of every 10 people who are said that they had cancer is actually being psyched out. They don't actually have cancer. It was a false positive, right? That was like J.C. Himmelberg. He was the 1 in 10, okay? A true positive test result is 80%, okay? So true positive is 80%. False positive is 10%. That is a positive test result given that cancer is present. A positive test result, cancer is not present. Okay. Confusion. All right, let's fill this table in. Here we go. Cancer, no cancer. We have positive tests, negative tests, and then we've got our total rows. I'm going to also probably do a total row down here at the bottom. Okay. We know that the chances of cancer are 0.01. So 1% of the population has cancer. Here's what I'm going to do. To fill this table in, I always try to pick on a really huge number down below here. Let's go with 100,000. Okay, let's say our total was 100,000. Okay.
What's the difference of doing just 100 to keep your numbers nice?
We could probably do 100 in this case because our numbers are 1%, 10%, 80%. Maybe 100 would work. Should we do 100? Let's try and see if we end up with any decimals. Typically, sometimes when you go to do the very far corner and you use a smaller number, you'll end up with a decimal.
Yeah.
And we don't want decimals. I don't know. Should we do 100? Should we try it? Let's try 100. We might be okay if we do it 100. And some of these other ones that you have, I think there's one on your homework assignment that's you have a 99.8% or whatever, then you want to use a larger number because you don't want to end up having to deal with decimals. Okay, so we know that 1% of the, we're going to end up with decimals if we use 100. Can we do is that 1,000?
Sure.
Let's do 1,000 instead. 1,000. I'm going to keep changing. Okay, 1,000. All right, we know that 1% of those people have cancer. So cancer, the total number of people that have cancer is 1% of this number. What's 1% of 1,000? 10, right? 10 of those 1,000 people are gonna end up with cancer. So I'm gonna put that in the total row right here. 10. Now, how many people do not have cancer then? 990, right? Okay, we know how to fill this table in. Got it? Okay, now a false positive is 10%. 10% is a false positive. So where's my false positives? No cancer positive test result. This is a false positive. False positive, okay? And that is happening 10% of the time, which means a true positive, a positive given that it is not present. So a true positive would happen 90% of the time. Is that where I want to put that box? Yes, I think so. That's a true positive.
What says the
It should
true
be
positive
80%.
rate is 80%?
Oh, wait. I want to put the 90% over here. 90% goes over here. Yeah. Okay, a true positive would be 80% of the time, and then 20% of the time is a false negative. Do we see how that works? 90, 10, 80, 20. Okay. So this is a false negative. I'll flag him. False negative. Okay. Now, 10%, what do we take 10% of?
The 9.
The 990. What's 10% of 990? 99. Okay, if we would have done 100, we would end up with a decimal at that point. What's 90% of that? Or you could just subtract.
891.
891? Yeah, I think you're right. 891. Okay. 20% of 10 is 2. 80% of 10 is 8. Yeah? Okay, now, this cell and this cell are doing what they're not supposed to be doing. Where did JC live? Was he in the 2 or was he in the 99? He's in the 99, all right? So he was told he had cancer, but he doesn't actually, right? This is where JC lives. These people, what's happening to the 2?
They have cancer, but it doesn't show up.
Until, like, too late,
Until it's
right? Which one would you rather be?
False positive.
I would rather be in the 99. Even though you get your scared to death for a little while, you're at least getting stuff figured out, right? And then these people are not gonna have a good outcome probably until, I mean, maybe they will, I don't know. But yeah, not good. So total positive test results would be what, 107, and total negative would be 893, right? Okay, and then over there we have totals also. Okay, find the probability. So I do this table. They say find the probability that somebody has cancer given that they had a positive, right? This is what we're doing right here. Has cancer given they have a positive test result. We're just going to look at that number. We're going to see what we've got going on here. So positive, how many people are positives? 107 is my bottom number. How many people of those actually have cancer? 8. Okay? So of the people who tested positive, 8 out of 107 have cancer. Which means that, okay, go ahead and figure that out as a decimal. Let me just explain to you what these results mean.
0.0748.
0.074, so 7.4%. Okay, let me explain to you what this number means, right? Out of all of the people who test positive for cancer, 7.4% of those people actually have cancer, which means 92.6% of the people who have said that they have cancer don't actually have cancer. Isn't that crazy? Like the majority, like a high majority of people who actually say that they have cancer actually don't. It's just that they flag one test, right? But if we do the results again and we multiply that by, like we multiply it by itself, like 0.704, this is me getting a false positive, right? If I take that times 0.074, meaning I run the test again, what's 0.074 times 0.074? If I run the test twice, that's like that redundancy, right? A false positive, 0.074, would be what? 0055. That is 0.6%. That is less than 1%, right? So if 7.4% of the time, right? Like I'll end up with like a false result, whatever, right? That number decreases significantly if I run the test again. Oh wait, maybe I should have.
No, because they do have cancer and it was positive.
So maybe I should have, nope, I should have multiplied this, I should have doubled this one, right? The 0.926, if you take that times itself, 0.926, that's what I should have done.
Then it's 0.057, so that'd be like a 5.
0.057,
I
I don't think that's it.
0.857.
0.857,
0.926 squared.
0.926, point,
0.926 squared.
0.857. So now my false positive results go down to 85%.
That's still
Okay,
pretty
that's still pretty high though. Yeah. So like we just keep running that test. Actually, you know what? We did it right the first time. No, you're fine.
It's happening.
No, you're fine. 0.6%. No. I see what you're saying. Okay. So these are the people, if I run the test again, 0.0 or 0.6% are actually having cancer given that they tested positive, right? That means that 99.4% are like the other direction. I don't know. I didn't do that right. Either. Don't listen to me. Don't listen to me.
I don't need to understand.
Yeah. Anyway, so I don't know. I'm dealing with the wrong numbers. We're using the process of redundancy to try to figure out how, like, to make the test result more accurate. Whatever. Okay. I don't know. Definitions.
Can we do number 9 together?
Sure. Let's do number 9. Now that I've got myself, like, all wound around here in a I'm confused. Aaliyah's trying to connect to us. Okay, let's do number 9. Phone survey. Subjects for the next presidential poll are contacted using telephone numbers in which the last 4 digits are randomly selected with replacement. Find the probability that for one such phone, the last 4 digits include at least 1 0. At least 1 0. So we have 4 digits. 1, 2, 3, 4. At least 1 0. Okay, I want to find probability of at least 1 0. Right? Okay, at least 1 0 is going to be like super complicated. So instead, we're going to take 100% and we're going to subtract the probability of what's the opposite of at least 1 0? No zeros. No 0. Okay, so we got to find the probability that this phone number is not a 0. So what's the chances that this digit is not a 0? 9 out of 10. Okay, the chances that this one's not a 0? 9 out of 10. This one's not a 0? 9 out of 10, this one's not a 0, 9 out of 10. So you could take 0.9 to the 4th power.
See, that's where I got
65661.
confused. I had the
What is it?
0.6561.
0.6561. So I take 100% minus 65.61.
It's like 34 is what I got.
34.29%.
Yeah.
There you go. That's the probability that it has at least 1 0. 39. You're right.
I just
You're
put
right.
34.
34.39.
Is that fine?
Sure, that's fine. 34.39%. Okay? So when they say at least 1, you do the opposite of that and subtract. Right? The probability of nothing happening, of the no zeros happening. Good, good?
Just to turn it in.
You're done?
Yeah.
Look at you go. Sure,
Um,
that's fine.
How?
okay.
4,
So
3.
yesterday, Hallie was in the class. I think Hallie, you were the one. Mr. McClay told us that every guy gets prostate cancer, and I looked it up, and that's not true.
No, it's not.
Every guy gets prostate cancer
Sometime
at
in
Okay.
some point in their life.
Yeah,
and I was
I
like,
was talking.
uh-uh.